And if you plug in that Legendre transform in the path integral and use the properties of Legendre transforms, specifically that because of this relation, J is equal to minus the variation of gamma with respect to phi bar, then you can easily derive yourself the following relation, e to the I gamma. Sorry, let me call that pi so it's less confusing. So the quantum effective action, the one particle irreducible effective action, is given by a path integral over pi e to the is pi and then e to the I delta gamma delta pi bar, and then it's pi bar minus pi. And so if I was to put the h bars back in, there's an h bar sitting here and here. And if, for example, let me just compute this to one loop. So the standard one loop approximation is just a saddle point approximation to this path integral. And the way to do that is to write pi as the mean value of the field pi plus squared h bar times delta pi. So pi bar is the thing we're evaluating it in terms of. It's the basic, you can think of it as the mean value of the field. And these are the quantum fluctuations around it. And we're going to do the path integral over the quantum fluctuations. And when you substitute that in, this will equal e to the is. This one loop order, this will equal e to the is as a function of pi bar times integral, the path integral over delta pi. And then at saddle point order, we just need the variation of the action with respect to pi bar twice, delta pi, and these are really functions of position, so these are functional derivatives, and I should have all the associated derivatives over x and y in there. Now the key point is that at one loop order, the only thing that matters is the double variation of the action with respect to the background pi. But what this is nothing other than what I would call S2, the action expanded to quadratic order around this background. Now if I take, for example, the cubic Galileon, just to see how it works, so I'll write it back in terms of that other form. Lambda 2 plus d minus 2 over 2. If I expand this to quadratic order around the background pi bar, then the quadratic contribution will just look to form like a z mu nu, an effective metric for the fluctuations. And this is what we talked about before in terms of the Einstein mechanism. So you get effective renormalized metric, a sort of a wave function renormalization for the fluctuations. And this effective metric, z mu nu, depends only on capital pi, which is the Galilean invariant combination. So this quantity, which essentially determines the propagator for fluctuations around this background, is Galilean invariant. And in fact, you can easily then, so because it's Galilean invariant, this path integral is Galilean invariant. So that means that the quantum corrections you infer from them are Galilean invariant, manifestly Galilean invariant. But these operators that are sitting in here are not manifestly Galilean invariant. They're only Galilean invariant up to total derivatives. So all the corrections you generate from the path integral will be manifestly Galilean invariant. In other words, the Lagrangian associated with them will be Galilean invariant, which means that none of them can possibly renormalize these pieces. So, so that's the essence of the non-renormalization theorem. And that argument I just made is one loop, but you can show that that's true to all loop orders, and that's because both the effective propagator for the fluctuations around the background and the vertices are all manifestly Galilean invariant. And that's one way to derive this non-renormalization theorem. Now, what are the implications of that? Well, this has a non-trivial implication on the massive gravity theory from which this derived, because these parameters up here, the alpha ends, the beta ends, and the gamma ends, are all derived from the original parameters in the massive gravity theory, in particular the graviton mass, and the various other parameters that you heard mentioned yesterday, alpha 3 and alpha 4, which are not the same as these alphas, but they're related. But the key one is that the graviton mass itself is one of these parameters. It's implicit in the fact that the strong coupling scale is written in terms of that. So effectively what we're saying is the strong coupling scale itself doesn't get renormalized. So the physical, when you track that back to the massive gravity theory, what that says is that the mass of the graviton mass m, receives no quantum corrections in the decoupling limit. So there's a non-renormalization theorem for the graviton mass itself. Now, this statement is only true in the decoupling limit. It's not true in the full theory. So the decoupling limit is derived by taking the limit m Planck goes to infinity. And so what that tells you is that the corrections to the graviton mass must be suppressed by powers of m Planck. And that means that having a small graviton mass is technically natural. So technically natural, when you say something's technically natural, you mean the quantum corrections to it from matter loops, from pi loops, from graviton loops. If they are small, if the parameter can be chosen small classically, and it remains small after you compute the quantum corrections, then its smallness is technically natural. And that means there is no hierarchy problem associated with choosing that parameter to be small. So that differs from the famous Higgs mass and the cosmological constant hierarchy problems. That's one of the interesting theories about these kind of theories, is that having a small graviton mass, which is what you would want for cosmological applications of these types of theories, is actually technically natural. Any questions on that? We're going till 20 past, is that right? Or? Yeah, 20 past. Okay, so that's a little bit about the Galilean and some of the interesting properties associated with them. They're a very special structure. There's only a finite number of terms in any dimension. They have this non-renormalization theorem. They lead to second-order equations of motion. And now let me come back to how to construct a theory of massive gravity in any dimensions using this knowledge of the decoupling limit. Back to a massive gravity. So for simplicity, let's try to construct a theory of a massive graviton on Minkowski space. So the graviton itself is described by a spin 2 field, which we usually package in terms of the metric. But to construct the theory on Minkowski space, there must be a reference metric, which I'll write as f mu, which is just equal to eta mu. So there are two metrics in the game, and the object we would call the massive spin 2 field is the difference between them. So what would the Lagrangian look like for a theory of massive gravity? Well, you just try to go as far as you can, generalizing. So we want to start with something like a kinetic term, which looks like Einstein-Hilbert gravity. And there are reasons why it ends up having to be that that is the only possibility. But for now, let's just try that possibility. And to this, I'm going to add a mass term, m squared, times some unknown as yet function of g and f. So this is more than a mass term, it's really a potential. So it's some potential which is a function of the two metrics. It has to be a scalar combination of those two, so things like g min u, f min u would be acceptable scalar combinations of those two metrics, but otherwise we don't as yet know anything about what that particular combination is. So to try and constrict this theory, using what we know about the decoupling limit. Before I get to that, actually, so first I must talk about the Stuckelberg trick again, but now in the context of this fourth theory. So this is a little bit different than, say, the new massive gravity case and just the Fitzpatrick case, the linearized theory, because in this case, what the mass term does is it breaks full nonlinear diffeomorphisms. So when I perform the Stuckelberg trick to identify the degrees of freedom that survive in the massless limit, then I should perform, remember the Stuckelberg trick reintroduces the performs a gauge transformation and makes the gauge transformations themselves into fields. But now the gauge transformations should be those associated with full nonlinear diffeomorphisms. Now this reference metric clearly breaks full nonlinear diffeomorphisms because it's a fixed metric that doesn't change. However, it's extremely easy to solve that problem because what a diffeomorphism is just a change of coordinates from x mu to some function of x. And it's easy to write this down in a way that's manifestly invariant in the diffeomorphisms by writing this as d mu phi a d nu phi b eta a b. And now, written like this object clearly transforms as a tensor if phi is chosen to transform like a scalar. So these four phi's are the four Stuckelberg fields for the broken diffeomorphism symmetry that we can reintroduce in that way. And if we choose the unitary gauge, where phi a is xa, then this will just go back to this, which is essentially the form of f mu in unitary gauge. So unitary gauge is the special gauge in which you gauge fix the Stuckelberg fields back off again, but we're not going to work in that because we want to think about the massless limit of this theory and use that to infer what the form of this thing has to be. So to do that, we decompose. So that's the four diffeomorphism symmetry. But remember that the 5 components of a massive spin 2 split up into the 2 of a massless, which is associated. And for massless fields, you always have a gauge symmetry. In this case, it's a diffeomorphism invariant. We've reintroduced that. But you also have a massless helicity 1. So there must be another U1 symmetry in our system, as well as the scalar. So there must be another U1 gauge symmetry that we have to reintroduce to correctly identify the massless limit of this theory. And the way you do that is very much like before. So in the decoupling limit, the metric would be expanded like this, canonically normalized like that, whereas the Stuckelberg fields are expanded with the same normalization that we chose before, over m squared m Planck to the d minus 2 over 2. So this nonlinear Stuckelberg field is capturing the Listy 1 and the Listy 0, and the metric is capturing the Listy 2. So why is that the correct thing to do? Well, let us reconstruct back the massive spin 2 field, h mu nu, which is g mu nu minus f mu nu, which now in this Stuckelberg form is g mu nu minus d mu phi a, d mu phi b, beta a b. And if we plug in those decompositions and expand this out to first order, then there'll be an eta coming from the xa here, which will cancel the eta that's sitting inside G. And in linear order, what survives is the H from here. And then from within here, when one of these is xa and the other is a, you'll get d mu a mu plus d mu a mu as before, so there's no m there. With the m normalization. And then from here, you'll get the d pi terms. You'll get d mu pi over m squared m Planck plus nonlinear pieces. So this decomposition, which introduces a U1 symmetry, is the right decomposition to reproduce the decomposition we know we need for the Fields-Pauli theory, and for the massive in terms of each of the guys and their appropriate normalizations. Okay, so now I'm going to take the decoupling limit of this massive variety theory. I don't know what the form of U is yet, but let's just take the decoupling limit and see what happens. So the decoupling limit as m goes to 0, and Planck goes to infinity, with lambda plus d minus 2 over 2 fixed, so just lambda fixed. And in that limit, if you look in order, so m Planck goes to infinity, so g mu nu just becomes e to mu nu at leading order. Okay, we'll just look at the leading order piece for now. The full thing you have to go to subleading order, but let's just look at the first piece. So g mu nu becomes e to mu nu. Phi, in that limit, although it's not entirely obvious, this is actually m over lambda to the 2 plus d minus 2 over 2. So this actually goes to 0 because of the m on top, and m is going to 0. So this becomes negligible, and the limit is designed so that the only thing that survives is the Licity 0 mode. That's how we set it up. I'll now write it in terms of lambdas. So that means that f mu nu in this limit becomes, just built out of this thing, it just becomes e to mu nu minus 2, and then, so f mu nu, remember, has derivatives of phi, so when we differentiate this, this just gives a delta, but this will then give two derivatives of pi, which is the quantity we called capital pi before. So this will give you capital pi mu nu plus capital pi mu alpha, capital pi alpha nu. And you'll notice that that's just basically eta minus pi squared, modulo the raising and lowering of indices. So now let's look at what happens to the mass term as we take that limit. So the mass term, of course, has to have m squared in front, and then the m Planck sits out front there. So if I just look at the contribution from the mass, we know what happens to this in this limit. It just becomes the Lishnerowitz operator, the spin 2 part. Let's look at the contribution of the mass. And now write m squared m Planck to the d minus 2 is the same as m Planck to the d minus 2 over 2, lambda to the 2 plus d minus 2 over 2. And then the root minus g just becomes 1, so we can ignore that. And then what we'll get is integral dx u to be just a function of e to mu nu and this f mu nu in this form. Right, in this form like that. And remember that we're keeping lambda fixed in the limit, but m Planck is going to infinity. So if this thing looks like, if this thing is finite, this thing is going to infinity, which is bad. So that's then we would have a problem. So if this goes to infinity, then the decoupling limit that we're taking would be bad. But the resolution is, if this thing is a total derivative, then this limit is okay, because we could just integrate by parts, and if we ignore the boundary term, as we're doing at this level, then this thing would be 0, and we would have 0 times infinity, and that would be a consistent limit, at least, and then we can go to next subleading order and check that that works out okay. So that tells you that this combination has to be a total derivative. Otherwise, the decoupling limit does not make sense. So the most general form of u is the most general form of functions of capital pi, the tensor, which is a total derivative. But we know precisely what those are. They're nothing other than the characteristic polynomials. So u, whatever that u combination, has to be a superposition of characteristic polynomials, which, if you remember, are these combinations which are which are given by the 1 over e minus n factorial and factorial, epsilon, epsilon, and then eta to the power of d minus n pi to the n. So if it's not immediately obvious to you that those are total derivatives, let me just think of the simplest example. So in the case of S1, this is just the trace of pi mu nu. But if I write that out in terms of the actual, that's capital Pi. If I write that in terms of the actual field, that's box pi over lambda plus d minus 2 over 2. And that's obviously a total derivative because it's box pi. If I look at S2, S2 was the trace of pi squared minus the trace of pi squared, which, again, if I write that out in terms of the actual fields, that's d mu, that's box pi squared minus d mu d nu pi, d mu d nu pi. And again, that's easy to see. If I integrate by parts and I put that mu over here and the mu over here, that becomes box and box squared minus box squared, and that's 0. So this is a total derivative. And in fact, the characteristic polynomials are themselves the most general quantities built out of pi, which are total derivatives. So that means we almost have our answer, except this was written in the decoupling limit, but that's enough to infer the full theory, because the trick is to note that in the decoupling limit, f mu nu is essentially eta minus pi squared mu nu. And so we can rearrange that in the decoupling limit. Eta mu nu minus pi mu nu is basically square root of f mu nu. Well, actually, it's not quite that. I should be a little more careful about raising and lowering of indices. So let me do that actually. So let me write this out slowly. So let me raise the first index, so it's written like this. F mu nu is eta mu nu minus 2 pi mu plus pi mu alpha pi alpha nu. And now it actually makes sense because the first index is always up, the second index is always down. So now it truly is the case that pi mu nu is equal to, let's get the right way around, eta mu nu minus square root of f mu nu. And that prompts then the non-linear, remember that u has to just be a function of u of g and f. So the unique covariant object, the generalized this, is this. It's what we usually call k mu nu, where I now replace eta by the metric. And I do the raising and lowering using the metric. And so that tells us what the full theory has to be. In order to have a well-defined decoupling limit, the mass parameter here has to be symmetric, a superposition of symmetric polynomials built out of wait a second, so symmetric polynomials built out of the pi's, and the pi itself is then written in terms of the k's, so built out of the k's. And this is precisely these ghost-free massive gravity theories that Rachel wrote down already, and it's precisely these combinations that are the objects that when you write it in Vierbein language, so E bar, if E bar is the Vierbein associated with F mu nu, and E is the Vierbein associated with G, then these symmetric polynomials are precisely the combinations she was writing down: E wedge, E wedge, E wedge, E, E wedge, E wedge, E wedge, E bar, E wedge, E wedge, E bar, wedge, E bar, etc., etc. And I think she'll talk more about that later. But in terms of the metric language, you can go from the Vierbein back to the metric, and it was originally discovered in terms of the metric. But the only downside of the metric language is you have this square root, which is precisely the square root you get when you go from Vierbein back to the metric language. So I'm running out of time, but let me just convince you that these are really the natural objects. And just let me show you that you do indeed reproduce the Fields-Pauli mass term. So let me go back to unitary gauge, where F mu nu is eta mu nu. Remember the Fields-Pauli mass term, the Fields-Pauli theory is usually phrased in unitary gauge. So in unitary gauge I just turn F to this, and G mu nu is eta mu nu plus H mu nu in unitary gauge, the normalization. So this object, K mu nu, is sorry, this is actually built out of the, this object, let me write it, I'll write it like that. This object is then eta mu nu minus square root, the inverse of this. So that's the inverse of eta plus h over length to the d minus 2 over 2 times eta. And if you expand that out at lowest order in h, so we've got an inverse here, so you get a 1 minus h. The 1 cancels this 1, because eta up down is 1, and then you basically get a half. So this gives you at lowest order h mu nu over 2.